Thanks very much. Yeah, my name is Brian, and Haskell is eating my Rails app from the inside out. I'm going to tell you why. Okay, so I work for a company called NoRedInk, and we make software for English teachers in the US, and that helps their students to learn grammar and essay writing and various things like that. And what we're going to talk about today is gradually migrating our backend language from Ruby to Haskell. And we've tried two different ways of doing that. I'm going to go through both of them. We first of all tried a services-based approach. So that was where we had one Ruby-only service and a few Haskell-only services. We'll talk about what worked well with that structure and what didn't. And then a different approach we also tried, which is the main focus of the talk, and that's going to be about language interoperability or foreign function interfaces, and where we have Haskell and Ruby in the same program. And we'll talk about some of the practical problems that solves and how it works. And so the main target audience I'm thinking about for this is if you're a functional programmer, you're working in an object-oriented or imperative code base at work, and you're either switching to functional programming or thinking about it, then this will be right on target for you. That doesn't describe everybody here, but there's going to be something in it for everybody. We're going to touch on a lot of different areas. Okay, so first I will talk a bit about the background to this project, how we got to where we are. I'll go through that services approach and the language interop approach and talk about the outcomes we got. So that's the overall structure. So Rails. Ruby on Rails is what the company was founded on. We started back in 2012. I say we, I wasn't around then. But yeah, 13 years ago in 2012, we started with Ruby on Rails, which was the big popular thing at the time. And the reason for that was for getting, it's optimized for getting up and running, and which it did. And it got us to where we are today and got the business off the ground. What a lot of people find with Ruby on Rails is after a while, once you've gotten up and running, so a few years into it, it can become a little bit harder to maintain. And so, yeah, we ran into issues like endless fire hose of runtime exceptions all the time, and there's a lot of implicit dependencies and things, so when you try to fix one problem, you kind of tend to find 4 other problems pop up somewhere else, and it just becomes a little bit of a difficult problem to try and deal with. And so why did we pick Haskell? Well, we actually had some previous success with another related language called Elm on the front end. It's kind of from the same language family. And a lot of what we liked about that was also available in Haskell. So the static types mean we can do confident refactoring. So if you move code around, once the type checker is happy, it tends to kind of work. So you can refactor more easily. You get explicit error handling and explicit side effects, so you can track down where your bugs are more easily. Also, contrary to what a lot of people think, we found this really good for hiring because good engineers tend to come looking for us rather than us having to go looking for them. So some of the constraints we're operating under here, we've been around for a good few years, as I said, and the code base has gotten quite large at this point. We've still got quite a small team. So there's way too much code to just, do one project that migrates everything and, don't work on customer stuff for a while and then just do that and then go back to that afterwards. No way, this is just completely out of the question. So this is something that we're expecting to take many years. And it's okay to leave some of it in Ruby. So there are parts where it's working fine in Ruby, we don't actually have any problems with it, and it's not actually a big value add for us to migrate that. So it's not just a full migration we're talking about, it's a little more involved and complicated, partly because of the size of the thing. And so we need to migrate our programming language while still building product features. So we need to migrate a little bit, do some product feature work, come back to migrating, go back to product feature work, etc. Now, like I said, we had already adopted Elm previously to starting this, good few years ago now. And we knew we had some experience from that, so that we knew going into this. And some of the challenges we ran into with that were the development is much slower initially because in the new language, you don't have very much to build on. Whereas like in the old language that you already had, there's tons of code that you already wrote and you can reuse it. And so every individual piece of work you want to do is going to be faster in the old language. because there's more of it around. And so that's a challenge to trying to switch languages that we knew about, but we were able to overcome it, migrating to Elm on the front end. And there's also obviously a learning curve with a new language. Some people have to learn it from scratch, but we managed to solve that as well. There was enough people in the team that knew it and managed to get it done. And so that was a big success. We were able to blend the language migration with the feature work to the point where Elm actually surpassed JavaScript in 1 year and even surpassed Ruby in 2 years. So this was, big success. Okay, so let's look at introducing Haskell into the back end with the services approach. Okay, so this is just the most obvious thing you would think of with introducing a new back-end language. You create some Haskell services outside of Rails, and the services can talk to each other over HTTP, and you try to write the new code in Haskell. That was our main kind of guideline, really. So some successful Haskell projects that we had, there was a service that we built that was to do with third-party API integrations. So there's other platforms in the education technology space that we integrate with, and we built services to deal with that were in Haskell. That worked really well. Actually, Haskell was much more suited to it than Ruby, so it worked out really nicely because Haskell does asynchronous I/O and Ruby can't do that, it just blocks. We had a tutorial service, so tutorials on our website are to do with like teaching a student a particular grammar concept, maybe the future tense or something like that. And they tend to be little standalone mini apps that walk you through the concepts. And because they're kind of standalone, it made a lot of sense for a separate service, and that worked out really well. And we also had this quiz state management service. So we have a thing called quizzes on our site where the students get a lot of questions about various different points of grammar, and they answer them, and so it's writing really fast to the database because there's millions of students using this feature. The Rails database layer wasn't really able to handle it, so we had to build a separate state management service, and we did that in Haskell. That involved extracting the bottom layer out of Rails for that part of the site. And so what all of these successful projects kind of have in common is that there were clear architectural boundaries. Now, in the first two cases, those boundaries were kind of obvious just from the definition of what the project was. In the last one, we had to do a lot of work to create that boundary, and we sort of made use of one that was already there in Rails, where the model layer deals with the database. But that's the common factor that we found for all the places where it was really successful. Areas where we had a lot more challenges with switching language were, well, there were some areas where we felt like we were really trying to force new code into a separate service, because a new user feature is not the same as a new architectural unit. So most feature work that we end up doing from 1 year to the next are very incremental. So what you end up doing is mostly changing code that was already there and maybe adding a bit of new code, but the idea that we went in with, that we'd put the new code over there and the old code over there, it didn't really work out like that in practice. That's just not how things go. It's not what the work that we wanted to do. We ended up with some boundaries that between services where it was really based on language rather than purpose. And it got very confusing to understand what the code was doing. And you also find that if you're splitting things up, if you're splitting a piece of functionality up across a couple of services, things can get complicated with database transactions where if you do some work over here and then do some work over there, and then you need to roll it all back, that has to get coordinated, and it's very hard. And another area where we had issues were to do with internal dependencies. And for that one, I'm going to just go through an example. Okay, so the example I'm going to use is taking a controller and moving it from Ruby to Haskell. So a controller, maybe not everyone here works in web, so I'm just going to go through that a little bit. The Rails framework is based on the MVC architecture, which is Model View Controller. And out of that, The controller piece is basically a collection of related endpoints, or it's handlers for those endpoints. And so an endpoint being a URL or a root in your application. And so that's something that makes semantic sense together, and you might want to migrate it together. And a controller tends to depend on other code. It needs to call into other code to work. And so part of that is the view. So your view is going to be your HTML template, where you've got a template you need to stick some data into. We're not going to talk very much about templates because we just haven't had many problems with that side of things. There's also domain logic. Some people call this business logic. This is about shared code that has something to do with the concepts in your business domain. So stuff, for us, that's stuff like grammar questions and schools and school years and all of those type of things that are related to our domain. And the final layer that the controller depends on are models, which are the database access layer. And so if we look at this kind of, I've drawn a sort of cartoonish type of sketch of a simple Rails app that's very small, like hundreds of times smaller than our real one, that has only 3 controllers and 3 models and about 10 files. Each of these squares represents a file, about 10 of them in the middle representing the domain logic. This ratio was about right. It's just a lot smaller than our real one. And I've labeled the controllers A, B, and C, and I've put numbers on the other files. So you can see the controller A is depending on domain logic number 1, 2, 5, and 9, and model number 1. And then we might have some other controller B that is depending on some slightly different subset of the domain logic and the models. And if we look at those together, we can see that there are some of them that are common to both, where the A and B aren't calling all the same into all the same files, but some of them are shared. And I've colored those in purple and marked them with A and B there. And that shared code is a good thing. That's a good practice that we want. And so this could be things like the user class or the school year class or stuff like that. That's common to loads of different things that might be otherwise unrelated. So let's say now we want to take controller B and extract it out and put it into a different service in Haskell. So what happens when we do that? There's 2 things that you notice when you do this. One is you've got to migrate all of your dependencies. So everything that B depends on has to also go into Haskell so that it can actually call into that stuff and it can work. And so, so first of all, you've got to migrate everything. So that's a big chunk of work. And secondly, you end up duplicating all of that shared code. So like I said, there were 3 files here that both of these controllers were calling into. And they need to exist in both the Ruby side and the Haskell side. So you now have 2 copies of a lot of these pieces of code. Now, what's even more complicated about this is that in Rails, it's actually very hard to even identify those dependencies. By just drawing that diagram on the previous slide, I kind of led you to believe maybe that I can actually draw those for the real code, but actually even drawing it is quite hard because Rails code doesn't need to use the require keyword in Ruby. So normally in Ruby, you have this require keyword that tells you, okay, I need to require stuff from some other file over there, and then I need to use it. So here in that example in the bottom, I'm requiring some other class and then using some other class below. But Rails does an automatic implicit thing here where it lets you get away with not doing that for the kind of convenience of writing it for the first time. And then I believe what it does is when there's an error because it doesn't know where that is, it goes and finds it using a convention about where files are located. So yeah, that's fun. So this is designed to be easy to write and easy to get up and running, but it's really not designed to be easy to analyze, and it's just a nightmare to try and figure out, even drawing the diagram on the previous slide. So, what does that mean? Well, like I said, we're duplicating a lot of this shared code in both of the servers. So that makes it very difficult. So we can't delete the Ruby one. So after we've migrated some code from Ruby to Haskell, we can't delete the Ruby one. We need to keep both of them because of the implicit dependencies. That makes it very hard to prove that the shared code is not needed anymore, which means you can't delete the Ruby after you ported it to Haskell, which means now you need to make any changes you make in those from now on. You kind of need to copy the changes into both languages. And like I said, this is a project that could take years because we've got a small number of developers working on a big code base, and this is a problem. So we were trying to fix maintainability by using Haskell, and now we're running into a major maintainability problem. Okay, well, what about if we just only do new domains in Haskell and the old domains stay in Ruby? Like this was the original idea we kind of had, where we said we'd put new stuff in Haskell and we can leave some of the old stuff in Ruby. But the thing is, our business domains are pretty stable, actually. We've had grammar quizzes and essay writing for more than 10 years each, and we haven't really added that many new domains. There's maybe a couple, but completely separate things that don't depend a lot on the stuff we already have, it just doesn't happen very often. Like maybe every 5 years at best, but if we do that, it just doesn't get us much because everything works incrementally in practice. And so after those initial projects that were big successes, and we did succeed in moving some stuff, the momentum kind of slowed down a lot and trying to find new low-hanging fruit. The low-hanging fruit was basically all gone, and stuff slowed down quite a bit. And so we need to take a step back and figure out what's actually really going on here and do some sort of analysis on this. And after going through it all, we've sort of figured out that there's an issue here of language versus architecture. And so essentially, the problem that we have run into is language is not the only issue. And so language is a really important thing, and having a better language is good. But it doesn't automatically fix your architecture. That's just a separate thing. It's kind of just not really about language. And so the other thing we're doing at the same time is breaking up a monolith. And now lots of people break up monoliths. This is a common thing in software engineering. But nobody finds it easy. It is a really hard thing to do, just trying to draw those boundaries and extract stuff. And so it's something that needs its own dedicated focus, and doing it just as a side effect of your language choice is, hasn't worked out so well. So we're trying to break up a monolith and change the language at the same time, which is even harder than doing either of them individually, and they're both hard things to do in the first place. And now they're kind of coupled together. So that's kind of our analysis of what's happening. Which makes us think, like we previously did something really similar and it went really well, so what's happening? So we didn't have these issues with Elm, but in the JavaScript to Elm migration, we had a big architectural advantage in that we didn't have a single page app to start with. So single page app is where your entire website is all just one JavaScript application. We didn't have that. We had separate JavaScript applications on each page just to do the interactive bits. And because we had it split up that way, that was natural boundaries that were already there in our code. And so that made things quite a lot easier. It was still, tricky, but that was a big help. And the other thing that was a big help is the fact that JavaScript and Elm are able to coexist in the same program. There's a foreign function interface system for letting them coexist on the same page. And that made it easier to, do a piece at a time as you needed to. The other thing that helped was that it was further in the past when the site was smaller. The Ruby to Haskell migration is a bit different. So on the back end, it's a bit more monolithic, not broken up into little pieces like that, harder to find clean boundaries. And of course, the other problem is that Elm and Ruby and Haskell can't coexist in the same program. But this one kind of made me stop and think at some point and wonder, well, what if they could? This might remove one of the major barriers that we've been finding. Okay, so that brings me to the next section of the talk, which is language interop. This is the main part of the talk, so I'm going to break it down further into little pieces. So first we'll look at some of the general concepts involved in language interop, look at a simple example of it, and then generalize it, and look at calling both ways between the two languages. Right, so first concept to introduce is Ruby extensions. A lot of languages have something like this, but let me just show you how Ruby works. There's a lot of Ruby libraries out there that are very commonly used that are actually just wrappers around C libraries. So this is stuff like MySQL, OpenSSL, zlib. You'll probably recognize at least some of these names. And so a lot of those are just C libraries, and somebody made a wrapper around them so you can use them from Ruby. And the way that works is that the Ruby virtual machine loads up the compiled binary code for those C libraries as a dynamic library. And so a dynamic library is some compiled binary code that isn't an executable, but is rather loadable by an executable. It's a binary format that's defined by your operating system, and on different operating systems, it has different file extensions. And these are the ones for Linux and Mac and Windows. So Ruby also provides a C library to help you create these wrappers. And it's able to, that gives you some ways to make C functions look like Ruby methods and to define Ruby classes from your C code. And the way this works is, you can imagine the Ruby virtual machine, which by the way is a C program, loading up a bunch of Ruby files. So you write your code into text files, and it loads them up into its memory and interprets that code and creates classes from it. But it's also, the Ruby virtual machine is also able to load up binary code in the format I was just talking about, and that binary exposes an init function, and when it initializes, Ruby calls into, the VM calls into it, and init calls back into the VM and tells it what classes to create. And it uses this C library that is provided with Ruby to do that. And so all of those classes exist together in memory, and it's all in the same process. They all exist together inside the virtual machine. And so this doesn't have to be C, because it's just compiled binary code, and loads of languages compile to binary, including Haskell. So this can work. So we just get Haskell to compile down to a binary library, and there is a particular format of that you can choose that is loadable by a non-Haskell executable, so the Haskell runtime is included inside your library. And Haskell is able to interoperate with C, so it's able to use that Ruby C library that they provide us to call back into the VM and tell it what classes and stuff to create. So we end up with C kind of being a common language between the other two languages. So Haskell speaks C, Ruby speaks C, and so they can talk to each other. Incidentally, almost every language has interop with C because operating systems are generally written in C and provide their interfaces in C. So some of the benefits we can get out of this are that we can actually run both of those languages on the same machine in the same process. So there's no HTTP latency, which is nice. It's actually not our main motivation for this. The main motivation was more a maintainability thing, but it's nice to have. You do function calls between the languages, and you can pass data around that isn't serialized. So normally if you're sending data from one service to another, you would serialize it to JSON or some other format. But in this case, we don't need to do that. We get the Ruby objects with the methods on them. So you can't call methods on JSON. And this is really interesting for us. So if we can mix the languages on the same server, then we can do a much more gradual replacement strategy. So in the same picture that I had before, remember there are two controllers with different dependency trees, and we wanted to take B and put it in Haskell. Okay. So now, all of this code starts off as Ruby, but we can take one of these files and just turn it into Haskell. And because we're letting the two languages exist in the same program and just have be in the same virtual machine, it means that all of the existing Ruby code is able to call into that Haskell, doesn't actually know that that's Haskell. It's just able to call into that binary code as if it was Ruby. And so we can completely delete the old Ruby version of it and throw it away, and we don't have this long-lived dependency issue. And we can then do that for the next one, and 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 the next one. And now all of that is in Haskell where we wanted it, and all of the shared code is still shared. and the old Ruby code doesn't even know that we switched it out for Haskell. So this solves quite a few of the problems we were having. So in our world with the separate services per language, we had to migrate entire dependency trees at a time. But with the language interop approach, we can migrate it in just small pieces. And with the separate services, it was very hard to verify equivalence, so we couldn't really tell if we'd properly migrated the code. But now, with this, you can actually run your Ruby tests on your Haskell code. Because remember, if we can call Haskell from Ruby, we can also call it from our Ruby tests. And so we can use those to verify that we've actually done that job right. You probably want to also check it in production, but it's a good start to run your tests. We had to keep our shared Ruby for a long time, but in this new system, we can delete it immediately. And we also had the problem with the separate services where we were splitting up database transactions between two different servers, but now they can actually share the same connection and share the same transactions, and that solves a lot of headaches. Okay, so let's take a look at a simple example. So here's a function, little toy function that we're going to use just to see all of the stuff that goes around it. It's called exclaim, and it takes a piece of text and adds 2 exclamation marks onto the end of it, for no particular reason other than to serve as an example. So we want to make this into a Ruby method and wrap up a Haskell function as a Ruby method. Okay, so how are we going to do that? First thing we need to do is take the argument values and convert them from Ruby data to Haskell data. Then we want to run our Haskell logic and convert the return value back from Haskell data to Ruby data. We're going to do that using this Ruby C library that I mentioned earlier on. That's part of the foreign function interface for Ruby. Now it turns out that in that library, all Ruby objects have the same type, which is value. There's this value type in C, and it's a 64-bit integer, which can either be a memory address or some encoded bits. And it's got some metadata in it about the dynamic type, but when the C code is compiled, it's all the same type, because again, Ruby is a dynamically typed language. Everything looks the same at the C compile time. And all of the functions in that library operate on this value type. So if we want to take a Ruby string, which would be our argument to the Ruby version of this function, and turn it into a piece of Haskell text so that we can run our Haskell function, then we can write a function like this, which is read Ruby string, takes a value, which is that, the C type that we saw on the other side, or a Haskell equivalent of it. Take that Ruby value and call a couple of C functions on it that we got from the Ruby C library, because Haskell lets us do that, so we're allowed to call C functions from Haskell. And that lets us get the C representation of a Ruby string, which is basically a pointer to where the characters are and the length of it as an integer. So we can get those by calling the Ruby C library, and then there's some Haskell foreign function interface related functions that we get. So this unsafe pack C string len, which you give it a pointer and a length, and it gives you the bytes, and you can decode the UTF-8 out of that, and you get your text. Cool. Okay, so we've gone all the way from a Ruby value to Haskell text. And we can go the other way too. Kind of skip through the details, but you do some UTF-8 stuff, and you go the other way. You take your bytes, you get the pointer and length, and you pass those back into the Ruby C library. So there's this Ruby C library gives you this RB UTF-8 string new thingy, which creates a new string that has UTF-8 bytes in it. And so remember, this was the simple function that we had as our example, and now we can make a Ruby version of that in Haskell. And so that simple Haskell function as a Ruby method, we can call it Ruby exclaim now. It takes a value, returns another value after doing some I/O operations. Talking to C counts as an I/O operation in Haskell. So you read the Ruby string, you get the text out of it. The read Ruby string is the function we just defined a minute ago. Run your original function, that exclaim function, get the result back, and create a Ruby string out of it. Well, that's cool for strings, but we don't just have strings, we need to do any other type as well, so how does that work? Well, in Haskell, if you want to do things that apply to lots of different types, you define a thing called a type class, And so we can define one for sending Haskell data to Ruby. And so this is called encodable. This encodable class is the class of all types that can be encoded as Ruby data. And so when I say encoded, I'm kind of thinking of Ruby as an external binary data format that we are encoding our Haskell data into. And so to be in that class, you need to define an encode function that takes that type and returns a value from it. And so the instance for text would look like this, where this encode function is actually the create Ruby string thingy that we saw on the previous slide. And we can go the other way as well. It's a decodable type class, so this is the class of types that can be decoded from Ruby data. And in this case, you also can get an error because that Ruby value might not have actually been a string. Maybe it was somebody gave you an integer or an array or something by mistake, and so you need to be able to return an error as well. And that means the read Ruby string that we defined earlier isn't enough. You kind of have to wrap some validation stuff around it. So check the with expected return type, runtime type thing, and the constant called string type ID, whatever. You just basically do some validation in case you got an error, and otherwise do the read Ruby string that we talked about before. And then you can take that type class and define other instances for it for all the other types that you need. So we have an internal library in our code base where we provide data converters for all the basic types, your strings and your booleans and your integers and your floats and all the rest. And some combinators to compose those together, and support for user-defined types as well. So things like arrays and hashes and structs and all those sort of things. And that means that our engineers never have to deal with all of that low-level data conversion stuff that I've just been talking through. That just gets defined once in a library, and after that you can write normal Haskell code. And so here's an example from our actual application where we have this thing called a catalog. It's part of our content management system. It's got a slug, which is a piece of a URL and a name and some content and an icon and various different things. And there's other user-defined types inside it. But all the engineer who worked on this had to do was add this line, deriving generic, and a couple of lines for instance decodable catalog and instance encodable catalog, and all of the Ruby Haskell conversion stuff kind of just happens by Haskell magic behind the scenes. Right, so then let's take a quick look at what one of our engineers would do to use Haskell from Ruby. And so just to remind you why you'd want to do that, this is in the case where you're replacing old Ruby with new Haskell and to make it usable from Ruby, so that's part of our gradual migration strategy. And also we might do this when we're creating new features in Haskell, but we want to put them inside the Rails app. And this is something we might want to do if there's if that new feature is closely related to existing Ruby code. So these are two situations where we might want to do this. And the way that we do it is we create a Ruby module, and in the Haskell side, this is just a value. So there's a type called a Ruby module, and it's a record with a couple of fields, so you give it a name. In this case, the example is JWE checker, so this is for checking web tokens that are encrypted. So it's got a name, and it's got a list of methods. And each method has a name, and it's got a Haskell function that implements it. And then we're calling this wrapper on the Haskell function, so this IO method 2. And that is the thing that does all of the data conversion, and it takes our verify function from Haskell and just wraps it up and does all of the conversion stuff that we talked about before. And we also provide some argument names for it. And then we run our code generation script that we have, and it generates this Ruby file. And the Ruby file contains a Ruby description of that same thing. So the class has the same name, JWE checker, it's got the same method name, verify, takes secret and token, and it does this call Haskell, passing in the name of the module and the method, and passing in the arguments. So this call Haskell thing here is a dispatch. So that's actually going to go into Haskell, and all of our modules are going to be in a big list, and it's going to look up the right one by module and method name and call that function with those arguments after doing the conversions. So let's talk a little more about this function dispatch, because that's not obvious that that's the right way to do it. We could have also just gotten it to define one Ruby method per Haskell function that we had. But actually, the way we've done it is through a dispatch. So there's this call Haskell, which takes the module name and the method name and an array of arguments and goes and looks up which function to pass that to. Why do that? Well, actually, the answer is that it just results in a lot less low-level programming for our feature developers to do. So when you're working on some feature, you want to be thinking about schools and classes and grammar and stuff, and you don't really want to be thinking about the low-level details of that. So that's library maintenance only. And this approach allowed us to do that a lot more easily. So now our feature development is all high level, no C code, no Haskell foreign function interface stuff, and no linker errors, crucially. If you've never had to deal with linker errors, then I am jealous of you. But yeah, when we're doing feature work, we don't really want that. So yeah, we just put all of our Ruby modules into a big list like this and make a lookup table from it and dispatch the right one. And the one last thing to say about that generated Ruby code is that we can also generate gradual types for it. So like a lot of dynamic languages these days, Ruby has a gradual type system where you can annotate the types of a method and like what the argument types are and what the return type is. And because this is generated from Haskell, we already know this kind of information and we can generate it as part of the Ruby code and just spit it out there. So that means we get full type checking across that language boundary. So you've got your sorbet type checker is telling you if your Ruby code is calling Haskell with the right types. So that's really nice. And let's look at the other way. So using Ruby from Haskell. Now this is a key architectural win to be able to do this because it means that new Haskell code can use tons of existing Ruby that we already have. We don't need to wait for all of that to get migrated before we can build new stuff on top of it. So how does it work? Okay, so existing Ruby code. So let's say we have this existing thing called a premades helper. Premade is a particular type of content that we have on our site. It's got a publish method on it, and it's got that sorbet gradual type stuff that I talked about. So that involves having a comment at the top of the file and requiring a certain library, extending a thing, and putting a signature on it. And we can add one more piece of annotation to all of that, which is this extend glue call from Haskell. And then we can write called from Haskell above any of the methods that we want to be called from Haskell. Okay, so this is how we annotate the existing Ruby code. Then again, we run a code generation script that generates this blob of Haskell here, which is a Haskell representation of that Ruby class with all of the glue code around it that needs to happen to make the calls. And so this wrapper is generated. It's calling into our internal library that does all of these helpers and type classes and things that we talked about, which in turn is built on top of that Ruby C library. So yeah, so now any of our other Haskell code can call into this, and that will wrap the Ruby module. Yeah, and you can use it. So there's lots and lots of useful code there that you can do. You don't have to wait for it to be all migrated to Haskell before you can use it. So that's how the language interop approach works. Let's talk a little bit about the outcomes from that. So we've had this in production for about 18 months without incident. We've put it into some fairly prominent user-facing features. So the assignment library is a key feature of the site. Teachers use it every day. We deleted a Haskell service and moved it into Rails because that was one of the places where we had a boundary that we didn't feel made a lot of sense. So it's together now with code that's related to it. So we can decouple these two ideas of which service it's in versus what language it's in. And we're able to test that JWE thing was for testing that our authentication works the same way in Haskell and Rails. In the development lifecycle, we're able to do code reloading in development. So you change a line of Haskell, recompiles, and appears in your Ruby app, which you can reload the page. We get error traces that are interleaved with names of Haskell files and Ruby files and how the error propagated through them. And we've got our monitoring set up for it. In terms of performance, people sometimes ask about this. So that data conversion we find it's faster than YAML, not quite as fast as JSON. We basically don't find it to be a major problem, but you do need to kind of plan so you don't have lots and lots of conversions. That function dispatch thing I mentioned is pretty similar to how a normal Ruby call works, actually. It does hash map lookups in the runtime. But the Haskell code is compiled and optimized, not interpreted. So the more Haskell you have, generally, it will tend to drown out those slowdowns from the data conversion stuff. And in most web apps, your performance is going to be dominated by how you use the database anyway. So for future plans, we are focusing on architecture first for the moment. So trying to do some general architectural improvements with how we do domain modeling and where we put our boundaries. Then we'll kind of go back to migrating old Ruby code. Hoping to open source this library, maybe this year, probably next year. So I'll just do a very quick recap if I have a second. All right, so we talked about the service approach. Where it worked was where we had clear architectural boundaries that were limited in scope, and it didn't work in a lot of other places very well. We had to migrate massive pieces of code, had boundaries in weird places and various other problems. The language interop enabled us to decouple the language migration from the service architecture and migrate smaller pieces and put the HTTP boundaries only where we wanted them and reuse our tests. The way we implemented that was with C as the universal language, using Ruby extensions, and of course those load binary programs that can be compiled from anything as long as you implement the right interface. We looked at how to wrap up functions and at how you can use Haskell from Ruby and Ruby from Haskell by generating code for the glue. I didn't have time to get into, there's loads of other stuff I could have gotten into, but didn't really have time. There's interesting things to do with memory management and exception handling, and I mentioned the DB connection thing a couple of times, but didn't really get into it because there wasn't time, and lots more stuff. But if you want to talk about that, we can talk about it after the talk. And so I just want to thank my colleagues who worked on this with me, Celso and Brian and Colin, Juan, Juliano, and Gina, who did lots of the work as well, particularly Celso. Brian was the main user of the code internally, and Colin is the manager who has been pushing a lot of internal tech improvements. So, yeah, thank you very much, and if we have time for Q&A, we'll do it.
Thank you. Applause! Now, we don't have much time before keynote. We can take one question. So, first come, first serve.
Hello. So I wanted probably to ask about the memory management. Do you hear me?
It's a little bit muffled. Sorry, could you speak up a little bit, maybe?
Okay. I wanted to ask about memory management.
Yeah.
Particularly, so for instance, in Haskell, when you make a say foreign call, you need to pass binned memory, etc. So it's not moved during garbage collection. Did you have anything about it in your consideration? Did you have to account for that?
Okay, I didn't catch every word, but I think you're asking about memory management, and was there any problems with passing data from one language into the other? Yeah, that worked out. I was terrified of that going into this project, but it worked out much easier than I thought. So basically, the trick is that when Ruby is doing a call into foreign code, it is guaranteed to keep those values alive for whatever's on the stack, or whatever you're passing in as arguments is kept alive for the duration of that foreign call. And so it's not going to be freed before it returns. And so, and all of the Haskell code, because it's pure functional, is actually kind of guaranteed not to have anything that lives past the length of the call either. So the lifetimes actually all work out quite nicely. So yeah, that's the short answer, I guess. Yeah, we in a lot of cases we're just copying data from one language to the other as well. So you don't we don't have yeah, dangling references and so on like that. I can talk to you more about it afterwards if you like.
Thanks for that. The rest of the questions have to go off stage. So one more round of applause and let the other people in.